Hello, good day. I'm Adelani, and I welcome you to our lesson notes on topic 4. We are on week 4, and I really want to appreciate all of you for your efforts. And my prayer is your effort will not be in vain. Let me fix my mic so that you could hear me properly. All right. So, and I want to believe that you are hearing me properly now. I just welcome you to week 4. I will be talking on this our lesson note on topic number 4, which is information representation. Information representation. And I remain my humble self, Adelani. And as a form of introduction, as you can see on the screen, computer does not understand human language. It doesn't understand any human language. It doesn't understand any data. It doesn't understand any letters, symbols. The system doesn't recognize pictures, audios, videos, and so on. Feed to computer. They need to be firstly converted into something that we'll call machine language. That's what systems, computers understand. That is machine language. Now, our objectives are only stated 3 here. We should be able to define what is a bit and byte. We should be able to understand the computer numbering system. Then you should also be able to manipulate binary numbers. We talk about binary systems, binary numbers. Should be able to do some little mathematics there. As a form of prerequisites for this course, for this topic, and for your previous knowledge, you've been taught about problem solving, where we dealt so much on it in our week 3. Our content is all going to fall in these 4 categories. That is, we are going to look at bits and bytes, characters, we're looking at number systems, then conversion from one base to another. We are not going in details of it, but just a the top of it. Now let's quickly talk about the number system. When we are young, we are introduced to the concept of numbers. When we are young, when we are 2, 3, 4, we go to primary school, secondary school, we are introduced to numbering system. To a computer, everything is a number. So what system understands is what? Numbers. Like for the alphabet, pictures, sound, and so on, there are numbers in terms of system understanding it. And there are 4 categories. Number systems, they are categorized into 4. They are categorized into what we call the binary number system, the octal number system, the decimal number system, and the hexadecimal number system, which represent the value of 16. The decimal represent the value of 10. The octal represents the value of 8, while the binary represent zeros or 1. So those are the 4 different types of numbering system that you need to familiarize yourself with. The binary, the octal, the decimal, and lastly the hexadecimal. Let's take a look at how they are. You can see the number system. You have the system, you have the base, and you have the digit. You can see it has to do with these 2 digits. It has to do with base. The base is 2, the base is 8, the base is 10, the base is 16. In terms of the digit, if you calculate this is 1, 2, 3, 4, 5, 6, 7, 8 digits. This is 10 digits, while this is 16 digits. When you start from 0 to 9, then begin from A, B, C, D, E, F. That is the hexadecimal numbering system of computers. But we are not going into that. We are going to limit ourselves to this binary system. And that takes us to bits and bytes. So what do you understand by the word bit? A bit is the smallest possible unit of data that a computer can recognize or that a computer can use. You can see a bit is the smallest possible unit of data that a computer can recognize or use. Computer usually use bits in groups. We are going there and we'll see how the computer is actually making use of it. Then what about byte? Byte is what? Is a group of 8 bits. 8 bits. When you have 1, 2, 3, 4, down to 8. If they are there as 8, is what? It is a group. And that is what we call byte. They call them bytes. Half a byte is called a nibble. Just a nibble. Half of it, half of 8 is what? Is 4. Thank you very much. Half of it is what? Is 4. Let's begin to dig deep. Now let's take a look at this diagram. This is 1 bit. This one is 1 bit, 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 and 1 bit. If you calculate all of them, they are 8 in number. And that 8 bits is equal to 1 byte. So if we ask you, what do you understand by 1 byte? 1 byte means is equal to 8 bits. You have 8 digits. That's what it means. Now the table below show conversion of bits and bytes. So you need to understand this table below. You need to understand it because we might likely do some small calculation on it. I could ask you how many gigabits is, sorry, how many how many bytes is in 1 gigabit? This is it. 1024 megabit is equal to what? 1 gigabit. And down to pentabit. Remember I told us from our introduction last week to the topic last week, I said we are going to limit ourselves to pentabit, and this is where we are. So you need to know how to calculate, how to convert from bytes to bits. If I ask you how many bytes do you have in 1 gigabit, so it means you should be able to do the calculation. This one is equal to this one. The kilo is equal to 1 meg. This one is equal to this one. So if you want to get how many bits of this, you just multiply this by this by this. So that will give you a total number of bits per 1 gigabyte. So let's continue to move further. And this is a kind of a binary representation of the codes. It is in 8-bit code that defines 256 symbols. Given below is the extended binary coded decimal interchange code. Let's see how it looks like. You can see how it looks like for this extended binary code. It will represent alphabet. Alphabet A, it takes it to be this. Alphabet B, it represents it to be this. Alphabet C, it represents it to be this. Alphabet D, it represents it to be this. E to be this. Now, the logic behind it is simple. The logic behind it is very, very simple. If I ask you to give me what is a alphabetic representation of A and B, or if I ask you to give me how will the computer recognize B, that is B and E, it's very simple. It's just for you to give me all these digits, which is 1 0, 1 1 0 0 0 0 1 0. Then what is E? E is what? 1 1 0 0 0 0. 1 1 0 0 0 1 0 1. So that is the representation of E. And for the B, it is this. Let me open up a notepad so that you will understand what I'm trying to say. Now, if I say for B, which is BE, if I ask you to give me the interpretation in the terms of E, B, C, D, I, C, and what is that? I said it earlier. I said it is what? Extended binary coded decimal interface code. If that is what I want you to use, so if I now ask you to give me what is B, so indirectly what I am asking you is, how will the system represent this in the machine language? You know, B as a letter B is equal to 1 0 1 sorry 1 1 0 0 0 0 1 0, and for E is what? Let's take a look at it. E is what? 1 1 0 0 0 1 0 1. So if I'm asking you what is BE, so it's simple. It's just to give me the addition of this. I've copied it, I've pasted it, and what? The addition of this. So what the system is actually going to understand is this one and not this. If you type BE inside the system will only recognize it to be these digits, all these digits, all these digits. And if I ask you here, how many bytes do you have here? Remember we said a total number of 8 bits make a byte. So in here we have, let's calculate it together. This is 1 2 3 4 5 6 7 8. That's what? 1 byte. Another again, 1 2 3 4 5 6 7 8. So this is equal to what? It's equal to 2 bytes, because one byte is equal to 8 bits. Remember this, we said it. So what you have here is what? Is 2 bytes, because you have 2 sets of 8 bits in it, like that and like that and like that, as you can see. Also, if you type this heart, this is what the system will recognize it to be. If you type this and, this is what the system will recognize it to be. Imagine if you type Ade is coming. Ade is coming. The system will only recognize it to be what? It's very simple, as you've seen the coded interpretation up there. The system will take A to be what? It will take the A to be 1 1 0 0 0 0 0 1. So the Ade is going to take the Ade to be what? If you check up, as you will see, Ade is what? It will take it to be 1 1 0 0 0 1 0 0. Then what about the E? The E is here. We will take the E to be this. We copy it and you paste it. You can see all what you have here is what is Ade, but the system cannot recognize it to be Ade. It will only recognize it to be what? In zeros and 1. And if you check the bits, the bytes that is here, you have 3 bytes here. 3 bytes are here. So let's move further. That is all about that. Let's quickly look at the conversion before we call it a day. Conversion from one base to another. There are many techniques or many methods which you can use to convert numbers from one base to another. These are the steps which I want you to understand very well, because you are going to be converting from one base to another. Step 1 is you divide the decimal number to be converted by the value of the new base. We are going to look at it, but have this at the back of your mind that you divide the decimal number by the to be converted by the value of the new base. Number 2, get the remainder from this step 1 as the rightmost digital. That is going to be a least significant digit of the new base number. Step 3, divide the quotient of the previous divided by the new base. We are going to see how it looks like. Number 4, record the remainder from step 3. There will always be remainder. Just be keeping the remainder in or as the next digit to the left of the new number base. Then you are now going to repeat step 3 and 4, getting remainder from left to right until the quotient becomes 0 in step 3. The last remainder thus obtained will be most significant digit. If I ask you what do you understand by MSD? MSD means most significant digit of the new base number. Example, we are going to be looking at this decimal number 2910. We are going to convert it to binary. It's very simple. Let's take a look first before we do the practical. Step 1, we are converting it to binary. Remember what we said in step 1, that you are going to divide this, the decimal number, you are going to be dividing the decimal number by the new equivalent number, the binary, the number we are taking the base to, and which is what? We are going to be dividing the 29 by 2. That's why we are having 2 here. Then you repeat the same thing. By the time you divide 29 by 2, you have 14, which is 28. It remains 1. That's why you have 1 here. Now, you now divide this number again by 2. If you divide 14 by 2, you are going to have 7. No remainder. The 7 again, the result, if you divide it by 2, you are going to see 3 inside, remainder 1. If you divide 2 by 3, you are going to see 1, remainder 1. And if you divide 2 by 1, what do you have? You have is 0. And remember, you have the remainder to be 1, then you put the 1 here. That's how we got 1, 1, 1, 0, 1. That is how to convert from a particular base to another base. Now let's take a look at the example, and that will be it. That will be it. As mentioned in step 2 and 4, the remainder have to be arranged in reverse order so that the first remainder becomes the least significant digit number. You can see LSD and MSD. And the last remainder becomes the most significant digit number. This is MSD. If you convert 29 base 10 to binary number, it will give you this number base 2. Now let's take a practical look at how it is. We said, right, I'll clean up that. We said we are converting 29. We are converting 29 base 10 to binary, and that is the 29. Because we are converting it to binary, binary is 2. Anytime you see binary, by, B-I, by 2, it means what? 2. So if I ask you to convert 43 base 2, 43 10 to base 2, or 43 8 to base 2. Let's start from, don't let me make it complex. We are still just beginning. Let's start with 43 base 10 to binary number. So you are going to divide 43 by 2. Let's work with the one we've seen. 29 by 2. So what would that give us? How many can you find inside? How many 2 can you find in 29? You can only find 1, 4. And if you see 1, 4, if you multiply 2 by 14, that will give you 28. Remainder what? Remainder 1. That's how we got the 1. Now, divide again that 14 by 2. What will that give us? That will give us 7. Isn't it? 7 times 2 is equal to what? 14. And that will remain what? The remainder is what? Is 0. Because if you divide 14 by 2, it will give you what? 7. Nothing is remaining. Now, that's 7. Divide it again by 2, which will give us, it will give us 3. Because you can only see, how many 2 can you see in 7? You can only see 3. That was 6. So 6 minus 7, that will give us 1. So it will remainder 1. Now the 3 again, divided by 2. Why are you just dividing it by 2 by 2? The reason being that we are converting to binary number. And binary means 2. So if you divide, how many 2 can you see in 3? 1. It will remainder what? It will remainder 1. Because if you remove 2 from 3, it will give you 1. Now that 1 divided by 2, what do you have? Can you actually divide 1 by 2? No, that's why we have the 0. But still remember, we still have the number 1. You still have the remainder number 1. If you now say, okay, that is 0. If you say is 0, if you say is 0 by 2, what do you have? What do you have? It's a 0. So you stop there. You stop there. So now, how are you going to write this? You now write 1, 1, 1, 0, 1, base 2. That was how we got this number 2 down here. This 2 down here. So class, if you need further clarification, just watch the video again until when you understand, especially this mathematical side. Don't assume that you don't know it or you can't know it. It is simple. Once you follow what I have said, you watch the video, you also read through the lesson note. It's very easy for you to understand. So at this junction, I would like to say a very big thank you to you for watching. God bless you.